we have to see how nucleophilic substitution occurs in allylic substrate by SN1 mechanism, and also we have to mention about the reactivity as well as allylic rearrangement. So we can take one example of allyl chloride and subject it to solvolysis with the ethyl alcohol, that is CH2 double bond CH, CH2Cl. Allyl chloride is subjected to solvolysis with the C2H5OH and it undergo SN1 reaction, and the chlorine atom will be replaced with the ethoxy group, and the product is allyl ethyl ether. This is an example for SN1 reaction because the solvent the nucleophile used is a weak nucleophile. Nucleophilic substitution by SN1 mechanism depends only on the concentration of the substrate. So if the nucleophile is a weaker one, it will take up SN1 mechanism. And as per SN1 mechanism, the rate determining step is the slow heterolysis to form the carbocation, and it is the nature of the carbocation that determines the course of the reaction. So in this above reaction of allyl chloride with the ethyl alcohol, initially the allyl chloride undergo heterolysis where the CCl bond is broken, and that leads to the formation of allyl cation. And in the previous topics we have seen that allyl cation's stability is same as that of a secondary cation because allyl cation is a resonance hybrid of two different structures, so its stability is more. Even though allyl cation is a primary cation, its stability is same as that of a secondary cation, so it can undergo SN1 reaction as fast as by that of a secondary substrate. SN1 reactions of allylic substrates can show allylic rearrangement. We know in the first step of SN1 reaction carbocations will be formed. Carbocation that is formed in allylic substrate is allylic carbocation. So allylic carbocation can undergo rearrangement where the position of double bond and position of the positive charge can alter between two structures. So as a result, this allylic substrate, when it undergo nucleophilic substitution, we will get a mixture of two products because the positive charge may be present on the terminal carbon or on the other side carbon atom if our substrate is a substituted allylic compound or allylic halide. Example, in concentrated solution of sodium ethoxide in ethanol, when 1-chloro-2-butene is subjected to nucleophilic substitution, it will take up SN2 reaction because we are taking a concentrated solution of sodium ethoxide in ethanol. So SN2 reaction depends on the concentration of both the alkyl halide and the nucleophile. Here the nucleophile used is a concentrated solution of sodium ethoxide, means sodium ethoxide ion. Ethoxide ion is a strong nucleophile. So it takes up SN2 reaction, and SN2 reaction we know that it will not give any rearranged product because carbocations are not formed as intermediates. So if you take 1-chloro-2-butene as a substrate, you will get 1-ethoxy-2-butene as the product. Similarly, if we take 3-chloro, second example, 3-chloro-1-butene, if it is subjected to SN2 reaction, that is if you treat this 3-chloro-1-butene with a mixture of or a solution of sodium ethoxide in ethanol, we may get 3-methoxy-1-butene. That means we are not getting any unexpected or rearranged product because carbocations are not formed as intermediates. A rearrangement is possible only if carbocations or allylic cations are formed as intermediate. The same reactant, that is 1-chloro, if we take 1-chloro-2-butene, when it is heated with ethanol in the absence of sodium ethoxide or in the absence of any other base, it will take up which mechanism? SN1 mechanism, because ethanol, it is a weak base, weak nucleophile. So SN1 reaction depends on the concentration of only the allylic substrate or alkyl halide, or alkyl halide. It depends on the concentration of only the alkyl halide. That means it follows first order kinetics. First order kinetics, where the reaction is, the rate of the reaction is independent of the concentration of nucleophile. So in the second example, if you take this 1-chloro-2-butene and if you treat it with ethanol, simply ethanol, you will get a mixture of the two products. That is, you may get either 1-ethoxy-2-butene or 3-ethoxy-2-butene. What is the reason behind it? If you take 1-chloro-2-butene, it undergo initial, as the first step of heterolysis is heterolytic bond cleavage of CCl bond to form the carbocation. The carbocation that is formed is an allyl cation, so it can undergo rearrangement where the positive charge may appear on the terminal carbon atom or on the other side of the 3-carbon unit, that is allylic system. So once this carbocation is formed, the nucleophile simply combines with the carbocation. So accordingly, you may get two different products. Or if you take the 3-chloro-1-butene also, you will get the same mixture of products, because both the substrate, when it undergo heterolysis, gives allylic cations, and once this allylic cation is formed, it can undergo rearrangement. So the allyl cation formed from 1-chloro-2-butene on heterolysis as well as 3-chloro-1-butene on heterolysis will be same structure, will be having same structures, that is two contributing structures, and depending upon on which carbon atom the positive charge is present, you will get the product. So you will get a mixture of two products for both 1-chloro-2-butene and 3-chloro-1-butene by SN1 mechanism. So regarding the nucleophilic substitution in allylic substrates by SN2, allylic substrates are as reactive as saturated primary substrates, because it is primary. If it is an unsubstituted allylic system, the allylic substrate is primary only. You know that the main factor governing SN2 reaction is the steric hindrance, because there is an intermediate formation of a transition state. Intermediate product is not formed, there is a transition state which is getting pentavalent. So steric hindrance influence the rate of the SN2 reaction. So allylic substrate, actually it is only as bulky as an unbranched primary group. There won't be any kind of steric hindrance, may not be there. So alkyl group has a capacity for charge dispersal capable of or comparable to that of a secondary group, but without bulkiness, because allylic substrate, it is a primary too, so it will not produce any steric hindrance. So it can even take up this SN2 reaction. If the nucleophile is strong, SN2 reaction will also happen in allylic substrate. So it is the strength of the nucleophile that switches between SN2 and SN1 reaction in case of allylic substrate, because the allylic substrate can foster or they can take up either SN2 or SN1 mechanism. Now the next topic is nucleophilic substitution in vinylic substrate. Here we have to encounter vinyl cation, how it is formed, what is the ease of formation, how stable it is, etc. So vinylic system is a vinylic substrate means the substituent is attached to a carbon-carbon double bond. Such compounds are called vinylic compounds. So vinylic substrates, when it is subjected to nucleophilic substitution, the leaving group may be replaced with a nucleophile, but this reaction is not that much easy that of an alkali substrate. Vinyl halides are less reactive towards nucleophilic substitution than their saturated compounds. What's the reason behind it? in vinylic halides the CX bond is unusually strong. It is very strong. Why it is very strong? You know that in vinylic substrate the carbon atom is bonded to 3 other atoms. Doubly bonded carbon atoms are bonded to 3 other atoms, so it uses sp2 hybridized orbital, and compared to saturated compounds where the carbon atom uses sp3 hybridized orbitals, sp2 hybridized orbitals have more S character. So they are situated, sp2 orbitals are situated more close to nucleus, and the nucleus may be holding the electrons more firmly than that of an sp3 hybridized orbital. So it is very difficult to break this CW bond. That's why vinylic substrates are less reactive, because the CS bond is unusually strong. Because for this SN reaction, nucleophilic substitution reaction to occur, carbon leaving group bond has to be broken. So it is difficult to break that particular CW bond in case of vinylic substrate as it is very strong. And when we compare the heterolytic bond dissociation energies, in order to form vinyl cation from vinyl chloride, the heterolytic bond dissociation energy is 207 kilocalories per mole, and for ethyl chloride on bond dissociation gives ethyl cation, that is 191 kilocalories per mole. The heterolytic bond dissociation energy for the formation of ethyl cation from ethyl chloride, it is 191 kilocalories per mole, and for the formation of methyl chloride it is 227 kilocalories per mole. So that means it takes, when we compare vinyl chloride and ethyl chloride, it takes 16 to 18 kilocalories more energy to break the carbon halogen bond in vinyl halide than the corresponding ethyl halide. That means more energy is needed to form the cation, means it is the particular cation formed is also less stable. So vinyl cations compared to ethyl cation, that's a primary, vinyl cation is a primary, ethyl cation is also a primary, but ethyl cation it is more stable, it is comparatively easy to form this ethyl cation than vinyl cation. That is why these vinyl halides are less reactive towards nucleophilic substitution reaction. Irrespective of the nucleophilic substitution mechanism, either by SN1 or SN2, the rate determining steps involves breaking of the carbon halogen bond. For this SN1 mechanism as well as SN2 mechanism, carbon halogen bond is broken at the rate determining step. So the bond in vinyl halide is harder to break and reaction is slower. The difficulty of generating vinyl cation is the factor that makes this vinyl halides less reactive towards nucleophilic substitution reaction. So if you want to subject the vinyl substrate to undergo nucleophilic substitution, two criteria must be met. That one is, first one, there should be an extremely good leaving group, and second criteria is the vinyl group should possess or it should contain electron releasing substituents. And the most commonly used leaving group is triplet anion. So it is a super leaving group. Actually triplet means trifluoromethane sulfonate, OSO2CF3. So in a vinyl substrate where the leaving group is triplet trifluoromethane, that is CF3SO3, trifluoromethane sulfonate. Trifluoromethane sulfonate is a good leaving group because 3 fluorine atoms, they are highly electronegative and they are best capable of accepting the electrons and accommodating the charge. So they are the super leaving group. So if our vinyl substrate possesses a leaving group that is triplet anion, we can subject that vinyl substrate to nucleophilic substitution reaction. So as I mentioned, the powerful electron withdrawing fluorine atom helps to stabilize the triplet anion. Triplet anion is actually, it is the conjugate base of the strongest acid, trifluoromethane sulfonic acid. Trifluoromethane sulfonic acid, from trifluoromethane sulfonic acid, Actually, H plus can easily come out. That means that is a good acid. That means triplet anion, trifluoromethane sulfonate anion is the weakest base that has less capacity to hold H plus. That is why this trifluoromethane sulfonic acid is the best acid ever known. So this is the reaction showing this particular nucleophilic substitution of a vinylic triplet. From this vinylic triplet, the triplet anion easily come out as OTF minus and vinylic cation is formed. Once this vinylic cation is formed, it can immediately combine with the nucleophile. We know SN1 reaction depends on the stability of the carbocation, and the difficult or the rate determining step is it is the first step that involves the slow heterolysis of carbon leaving group bond. So once this carbon leaving group bond has been broken, particular carbocation will be formed, and the carbocation, as it is highly unstable, it is in need of one more pair of electrons. It will try to attain that pair of electrons anyhow. So the nucleophile can, even though the nucleophile being weak also, even weak nucleophile can immediately combine with the carbocation to give the substitution product. That is how the substitution in vinylic substrate is carried out. Thank you.